Chapter 3, Part 2. Let's talk about Copernican Revolution. So, our goals of learning for this part. How did Copernicus, Tycho, and Kepler challenge the Earth centered model? And what are Kepler's three laws of motion? And how did Galileo solidify the Copernican Revolution? These goals, if after this part of this chapter, you should be able to answer these questions. And these are the questions that could be similar to what you have in your exam. So, Copernicus proposed the sun-centered model, and he published his book in 1543. But what he used for the model, uh, you know, is something that we are still using today as a planetary distance based on the distance from the sun to the Earth, which is called AU, or astronomical unit. So 1 AU is one astronomical unit, which is about 93 million miles, and is the average distance from the sun to the Earth. Okay, average separation between those. So he used the model to determine the layout of the solar system, or planetary distance in AU. But the model was not more accurate than a Ptolemaic model that we had before in predicting the planetary position. And the reason for that was because he was using a perfect circles. So he was using the perfect circles for the orbit of the planets. Then Tycho compiled the most accurate ever, down to the precision of 1 arc minute, naked eye measurement of a planetary motions and objects in the night sky. So he still could not detect the stellar parallax at that point. And so he thought that the Earth must be at the center. And so what he did, he hired Kepler to use these data and kind of make sense of them. Okay, so Johannes Kepler was first trying to match Tycho's naked eye observation of planetary motion with the circular orbits, and then he found out that the data that Tycho has, which is very precise for this time, naked eye observation of planetary motions down to the precision of 1 arc minute, is not matching the perfect circular orbits. And there is an 8 arc minute difference between them. So he ended up eventually changing or moving from perfect circular motions of these planets to a non-circular motions, or ellipses. So for ellipse, we have something called eccentricity, and some of you might be familiar with. So a circle has an eccentricity of 0. And eccentricity is basically describing how much an ellipse is different, or how much it deviates. It deviates from a perfect circle. If you have, it can goes from 0, which is a perfect circle, to 0.99. So it cannot be 1. It could be very close to 1. 0.99 is the maximum amount it can have. And it will be a very high eccentric orbit for an object. If you have a perfect circle, the focus point or two focus points will be at the same spot at the center. If you go and have, let's say, a eccentric path or ellipse of eccentricity of 0.2, for example, okay, then you'll have two focus points right here. And for the planetary motions of comets, short period comets, motion of asteroids and things like that, sun is at one of these focus points. Okay, so let me very quickly share another file with you. So here we can kind of see, if I change the eccentricity all the way from 0 to 9.99, okay, I am going from 0. Now the two focus points is at the center of the sphere, okay, and I can also change the semi-major axis. So technically I can change the radius of this. So let's put them at, let's say, 20 AU. And then I can change the eccentricity, and you can see that how it changed the orbit, the shape of orbit ellipse. And this is what we have for the planetary motions. They are not perfect circles. The eccentricity is not zero, even for Earth. But it's for Earth, it is very close to being zero. It is not. It is not that we have a 0.2, 0.3, or whatever. It's very close to zero. So if you go on outer space and you're looking at the Earth's path, Earth orbit around the sun, just by looking at it with your eyes, you cannot tell that it is not a perfect circle. It's very close to a perfect circle, but it's not. There's a little bit of eccentricity. Okay. So let's go back to our PowerPoint. So here you can see that there are two focus points, and sun will be at one of those points. Now, there are three Kepler's laws, or planetary laws. Kepler's first law is saying the orbit of each planet around the sun is an ellipse with sun being at one of those focus points. And there are two terminologies I want you to remember: perihelion and aphelion. Perihelion is when the planet is getting closer to the sun. Okay, so right here. Okay, throughout its orbit, it gets close to the sun and gets really far away from the sun. So one is perihelion, the other is aphelion. Okay, so Kepler was saying that the first law is the orbit is a ellipse and the sun is at one of those focus points. Second law of Kepler: as a planet moves around its orbit, it sweeps out equal areas in equal times. And this is very interesting because this means that the planet travels faster when it is near the sun, and when it's really far away, it moves slowly. So in other words, this area here, okay, that I'm highlighting, and this area here, they are the same. When a planet is close, it has to move to cover more area in a short period of time. But when it's in the aphelion and it's really far away, it's moving slowly. So that's Kepler's second law. And we can kind of see it here. Let me share another screen very quickly with all of you, or go back to our animation. So Kepler's second law, take a look at this velocity. So let me go from around 0.5, eccentricity of 0.5, and take a look. So this is the speed, orbital speed, so, and then orbital radius. So I'm going to begin. As it's going away, we can see that the velocity here decreases. Okay, and then as it's getting closer to the sun, to perihelion, the velocity increases and the orbital radius decreases. Okay, so the Kepler second law, in other words, is saying if you're really far away from the sun and you're in a stable orbit, orbiting the sun, if you're really far, you're moving slowly. If you're getting really close, you're moving fast. And by the way, all of these are available. You can download them and play with them on your computer. Kepler's third law is saying that the orbital period of an object rotating around sun, let's call it P, it is related to the average distance from the sun in AU. So P squared goes as A cubed. The orbital period in years to the power of 2 equals to the average distance from the sun of that object to the power of 3. Okay, and we can kind of test this very quickly on our animation here. So let me go and test it here. So let's say that I want to stop that, reset it, and I want to start here, okay, and then I'll stop the watch here as well. So let's go ahead. Well, actually, let's just start here. All right. So we were just waiting to go one full orbit to see what we get in years. Then I have to stop when it gets back to here again. I am going to stop right now. Okay. So one more time. Reset. And We're just waiting for it to get here because it's easier, it's moving slower. Start. So we're just waiting and monitoring this time here in years that is taking it to one complete rotation. And we'll stop when it gets back to that point. Okay, so roughly 11, okay, 11. So this is the time in years that it takes this object to do one complete rotation. And what is the semi-major axis for this object? It is 5 AU. So A is 5 AU. Now, so A is 5 AU, right? And T, or orbital period, is 11 years, roughly. There's a rough number. So our calculations would not be very accurate because we're not using the exact number. So A to the power of 3 should be P to the power of 2. And let's take a look. A to the power of 3 is 5 to the power of 3, right? So it is 125. It's 5. It's 125 to the power of 3 cubed. P to the power of 2, 11. 11 to the power of 2 is 121, right? So 121. Kind of close. They're not exactly the same because we're not accurately measuring it. Plus, we later on update this formula with a better formula. So there's some terms here that are missing. But this is accurate. So this is the Kepler third law, as the semi-major axis, or the distance from the sun to the object to the power of 3 should be equal to the orbital period to the power of 2. Okay. Now, let's take a look. So if we kind of graph what we have, so starting from the average, on the x-axis, we have the average distance from the sun for all of these planets, for Mercury, Venus, Earth, Mars, and so on. So Earth is at 1 AU, which is 1 astronomical unit, right? And then the average orbital speed is about 30. As you get, if you go from the closest object to the sun away, you can see that the velocity of these objects drops or decreases. So if you're closer, like an object like Mercury, you're having a high velocity. As you go away to Earth and then Mars, your velocity decreases because you're going further away from the sun. For example, Saturn is in about 9.5 AU, right? So it's moving slower compared to Jupiter. And it's the same for the orbital period. So here we have the average distance again from the sun. And this little kind of box is showing here the inner part of the solar system with terrestrial planets, right? Mercury, Venus, Earth, and Mars. And then so here we map, or we try to fit a line for all of these planets where we have the orbital period in years. For example, the orbital period for Earth, okay, is 1. 1 year, taking us 1 year to do one full rotation. So we see that there is a perfectly straight line fit between these points. So that's why we think that P squared goes with equals to the average distance to the power of 3 or cubed. P squared equals to A cubed. Okay, but we will update that. Newtons actually update that later on. So a thought question: an asteroid orbits the sun, and you know what to do. You have to pause the video, work on it yourself, okay? So an asteroid orbits the sun at an average distance of about 4 AU. So the distance is 4 AU. A is 4 AU. How long does it take to orbit the sun? So we're looking for P. Okay, that's what we're looking for. We know the formula. We know that P squared equals to A cubed. Okay, so P squared here, which we don't know what it is yet, is equal to A cubed, and A is given. It's 4 to the power of 3. Now P squared is 4 to the power of 3. And what is 4 to the power of 3? 64, right? What number here? We're looking for P. We're not looking for, so here's the point that a lot of you make mistake. You see 64 here, and you go ahead and mark 64 years here. Okay, but this is P to the power of 2. We're looking for P, not P to the power of 2. We're looking for orbital period. We're not looking for orbital period to the power of 2. Okay, so what number to the power of 2 or multiply by itself will give you 64? It's 8, right? So the answer is 8 right here. Boom. So P is 8. All right. Right here. And here's the solution for it. Now, let's talk about Galileo. So Galileo overcame the major objections to the Copernican view. So 3 key objections for the Copernican view, there were that, I have them right here. So Earth could not be moving because objects in the air would fall behind or left behind. Non-circular orbits are not perfect, and so heavens are perfect, and that's what they were saying. And then the third one, if Earth were really orbiting the sun, would detect the stellar parallax. So Galileo overcame these 3 objections, and we're going to see how he did that. So Galileo experiment showed that objects in the air would stay with a moving Earth. Okay, because so Aristotle thought that the objects would naturally come to rest, but Galileo showed that the object could still be in motion unless there is a force acting on him. That's Newton's first law of motion. An object will continue moving or will continue being stationary unless there is a force involved to stop it. Okay, so if you have an object and it's moving, if there is no force acting on that object at all, that object will keep moving forever unless there is a force to stop that object. Okay, so that's the first overcome. And the second one, so he teaches observation of the comets and supernova and things like that were already challenging the idea of perfect. I don't know what the perfect means at that time, but so Galileo used his telescopes to, he observed sunspots. He lost his vision because of observing those sunspots. And he saw mountains and valleys and, craters on the surface of moon. So the idea of being a perfect heavens or perfect things like that were completely ridiculous after that. And so the third objection, the stellar parallax, Tycho thought that he had measured the stellar distances, so lack of this parallax seems to rule out the orbiting Earth. So he was thinking that Earth is not orbiting. But Galileo showed the stars must be way, way further away than what we think originally. So so we can't really see a stellar parallax with our naked eye because they're really, really far away. So we don't have the resolution to see it. Okay. So he was already seeing that there's a countless of individual stars in the Milky Way. So just to give you a review of what a stellar parallax was, we talked about it in our last video. But so let's take a look. If let's say that throughout the orbit of the Earth around the sun, you're looking at the nearby star with a fixed background of a distance of stars, and you're looking at it in this way. So that this is what you're seeing. Okay, 6 months later in July, you're looking at the same star, but you're seeing it's moved from this point to another point. So it was originally here in January, now it is moved. This is called a stellar parallax. In order for us to see a stellar parallax, we have to have enough resolution to see it. We have to have enough resolving power to see this, and that requires having a telescope. If you don't have a telescope, your eyes cannot understand this. You don't really see the difference between January and July because you're not having enough resolving power in your eyes. Okay, so that was one thing. And then Galileo see the moon's orbiting Jupiter. So that this is providing the idea of not everything is rotating around Earth. There are objects in the sky that are rotating around another object. And this is his handwriting as he was observing the moons of Jupiter. It's amazing. Furthermore, Galileo found that if indeed Earth is at the center, and you have, for example, Venus going through the Ptolemaic view of Venus, for example, or Ptolemaic orbit, then there are only two phases that you can see. You can see crescent on different phases of the Venus. But what we saw and Galileo observed was different phases of Venus throughout its orbit. And when it's very, very bright, you can actually see these phases with a very simple refractor telescope at home. Okay, so this is what Galileo was talking about: crescent, gibbous, full, gibbous, quarter, things like that. So different phases of Venus. He observed them. So he thought out, oh, the Ptolemaic view is totally wrong then. In 1633, the Catholic Church ordered Galileo to recant his claim that Earth orbits the sun. His book on the subject was removed from the Church Index of Banned Book in 1824, and Galileo was formally vindicated by Church in 1992. So I'm going to skip this part. We very extensively talked about this. This is just a review of what we've talked about in this part of the chapter. But I wanted to go here and talk about a little bit of a scientific method that we use. So in scientific method, we make an observation, we ask a question, right? You make an observation, so you don't really know what's going on, so you ask a question, and you suggest a hypothesis. And then, so based on a hypothesis, you make a prediction. And you perform a test. So that test either support the hypothesis that you have, which means that you can make more tests, you can perform more tests, or the test does not support the hypothesis. So you have to revise it and make a new one. So this is something that we do in our everyday life sometimes, and also in every science project. You make an observation, so you don't really know what's going on. You try to ask a question, make a hypothesis, and then you predict. You do some predictions. You test it. If it works, you do more tests, and if it doesn't, you change your hypothesis. So, but science sometimes rarely proceed in this idealized way. For example, sometimes you just start by looking and then coming up with a possible explanation without even doing anything. Sometimes we just follow our intuition rather than, a particular line of evidence. We just say, okay, we see this, so that means this, All right, now, what is the scientific theory? So the word theory has a different meaning in science than in everyday life. In science, a theory is not the same as hypothesis. The scientific theory must explain a wide variety of observations with a few simple principles. This is very, very important. If you're looking at the most complicated theories in physics, for example, the general relativity, things like that are generally very difficult to understand. Their outline are very simple. So you should be able to explain it with a few simple principles. And it should be supported by a large, compelling body of evidence, okay? And it should not fail any crucial test, okay? So these are the things that a scientific theory should have. So a thought question, again, pause the video, read the thought question, read the answers, choose your answer, and then play the video again. I'm gonna do the same. So Darwin's theory of evolution meets all the criteria of the scientific theory, and that means A, B, C, or D. Pause the video, think about it. All right. Which means after more than 100 years of testing, Darwin theory stands stronger than ever, having successfully met every scientific challenges to its validity. Okay. I'm going to stop here. This is the end of chapter 3. And then right after this, we'll go to chapter 4. Stay tuned.